Hello, my name is David Patterson. I'm a retired research scientist. I have a degree in applied mathematics, in engineering, and I have a PhD. I spent 2 years working on infinite numbers. And when I started that, one of the original aims was to see if I could get infinite numbers to solve unsolved problems in quantum mechanics. Well, I've been successful and I've been unsuccessful. What I have found is that infinite numbers of a specific type, called ordinal infinity, tie in very, very closely with what has already been done in quantum mechanics. But what I haven't been able to do is solve unsolved problems. Rather, I've been able to solve solved problems, as it were, using infinite numbers. The type of infinity that you were taught at school is not very useful. It has the property that infinity equals infinity plus 1. You can't divide infinity by infinity. And it's counterintuitive in a lot of ways. The infinity which I'm using here is called ordinal infinity. And one way of thinking of that is that we say that if something is true for a sufficiently large value of x, then it is true for ordinal infinity, and vice versa. This is part 4 of the talk. Parts 1, 2 and 3 introduced ordinal infinity, and part 3 introduced the fluctuation rejection limit, which was a way that can be used for solving indefinite integrals. Now for some quantum mechanics applications. Don't panic, I'm not doing anything that is exceedingly difficult in the way of mathematics. The only thing you need to be careful of is if you don't already know what a complex number is, then skip the section that I'm talking about quantum renormalisation, because that does rely on complex numbers. But the rest of it should make perfect sense. This is a review of the talk parts 1, 2 and 3. Ordinal infinity is not written using the usual infinity symbol. It's written using the lowercase Greek omega, which is the bottom half of the infinity symbol. Infinity is not equal to infinity plus 1 in this case. Infinity is in fact less than infinity plus 1. In parts 1 and 2, I gave 4 different ways to generate the field of ordinal infinite numbers. In part 3, I noted that standard analysis contains 2 incompatible definitions of limit. One of these is appropriate for infinity equals infinity plus 1, and the other one is appropriate for infinity is not equal to infinity plus 1. And I use that as an excuse to introduce a new non-shift invariant, which means infinity is not equal to infinity plus 1, fluctuation removing limit, which means that I equate a pure fluctuation with mean 0 to a value of 0 at infinity. I've written this new limit as lim star, and that limit allows us to evaluate improper integrals that couldn't be solved before. As a use of lim-star, take a function, split it into a mean plus a pure fluctuation part, and define the limit as, for integers or for real numbers, the limit equals the limit of the mean value at infinity. Now let's move on to quantum mechanics. A chap called Abraham Robinson in the 1970s managed to prove that every infinite integer has a unique factorization, which is a pretty amazing thing to prove. And how do you factorize infinity? Well, you are free to choose whether any particular infinite number is factorizable by another. But if it is, then that affects infinity plus 1, it affects infinity plus 2, it affects infinity plus 3, etc. Now, rather than thinking of quantum number as a number of wavelengths in an interval, you can think of it as a modulus, i.e. the remainder after dividing an infinite integer by a natural number. Now this may be useful for free particles, because particles that are confined to orbiting an atom, it works to treat quantum number as number of wavelengths in an interval. But there are a lot of particles that we talk about in quantum mechanics that aren't confined to atoms. Suppose n equals 2. You're free to choose whether any particular infinite number is odd or even. But once chosen, the answer remains fixed for the remainder of the calculation. So if we choose omega to be even, then omega plus 1 must be the opposite, odd. Now, quantum mechanics has something similar. If two particles are in an entangled state, then one has quantum number 0 and the other has quantum number 1. But we don't know which is which until we observe one of them. Similarly with infinity and infinity plus 1. One must be odd and one must be even. But we don't know which is which until we observe one. So infinity, that is omega, exists in a multiple state of being odd and even at the same time until either infinity or some other number is some other infinite integer is observed. Now, the entangled particles may be any distance apart when one is observed. An observation then would give rise to what is technically known as spooky action at a distance. In wave-particle duality, the more accurately the wavelength is known, the less accurately the position is known. This is codified in the Heisenberg uncertainty principle. Now, in order to fit into the tightly constrained order of the number line consisting of real numbers, ordinal infinity, and infinitesimals, a function that specifies a wave has to reduce to a single point. A wave becomes a particle, and therefore you can treat this as a wave-particle duality. However, although the limit lim-star converts a wave into a particle, it doesn't do so in the correct way, because lim-star is deterministic. The process of converting a wave into a particle in quantum mechanics has to have a random element. Ordinal infinite numbers are a good way of doing this, but not through the operation of the limit lim star. Divergent series are often encountered in quantum mechanics. In perturbation theory, a series is produced. In perturbation theory, we look at Feynman diagrams. First level, first order Feynman diagram, we just have a simple interaction. For higher order Feynman diagrams, we have loops inside the diagram. Each loop that's added introduces another order into the solution. I'm going to explain this a bit more later. Anyway, the series that is generated by perturbation theory may converge or diverge. If the series does diverge, as is often the case of quantum chromodynamics. Now, quantum chromodynamics is the theory of quarks. Then one possibility is to use ordinal infinity to evaluate that divergent series, using the limit that I defined in part 2. So lim star can be used to evaluate a divergent series, such as potentially ones that are generated in quantum chromodynamics. But that hasn't been proved yet. Now comes the real difficult mathematics, and if you don't know what a complex number is, you might want to skip this section. The following mathematics comes from the book by Abraham Zee called Quantum Field Theory in a Nutshell. But instead of what he uses as a cutoff to remove Abraham Zee uses a cutoff to remove ultraviolet divergence. Here, what I do is replace that cutoff by ordinal infinity. This makes sense because the cutoff in quantum mechanics is defined as a sufficiently large real number, and so is ordinal infinity. We talk about first order, second order, third order. And that is that there's a parameter, a coupling parameter, lambda. And you can see little lambda here, little lambda here. As in Mary had a little lambda. First order has lambda on its own. Second order has lambda squared. Third order has lambda cubed. So let's look at second order now, which I've written as m subscript 2. Here k, the wave number, which is defined as 1 divided by the wavelength, is a real number like x. The wave numbers of the two incoming mesons are k1 and k2. The wave numbers of the two outgoing mesons are k3 and k4. And we want to find the strength of the interaction that generates a given k3 and k4 given k1 and k2. The Feynman diagram for the second order, that is the lambda squared correction to the meson-meson scattering amplitude, gives this horrible messy integral here. But I'm going to go through it a little bit. I here is the square root of -1. Lambda, at least I hope it's the square root of -1. If it's not the square root of -1, then whatever. still get the same answer. Lambda squared at the front, and inside we have 1 on k squared term there and a 1 on k squared term here. So that behaves like d to the 4th k. Now that's an integral to the power 4 because we have 3 space dimensions and 1 time dimension. D to the 4th k over k squared times k squared is k to the 4th. So this integral behaves like x to the minus 4 d to the 4x, which diverges logarithmically like the integral of dx on x. And physicists refer to this divergence as ultraviolet divergence because it happens at large values of k, large numbers of wave number, small values of wavelength. Now, next thing to keep in mind is this m squared term here. I'm going to ignore it because it's small. Set S equals the sum of wave numbers for the incoming particles, and that's related to the energy of the system. Set T equals that value and U equals that value, and T and U are related to the scattering angles. Two particles come together and then scatter out at different angles. C is a numerical constant. We calculate the wave number up to a maximum wave number of ordinal infinity. This is the change that I've made here. Instead of going up to a cutoff magnitude, I'm setting the cutoff magnitude to infinity. So everything should behave quite interestingly. I'm not doing the integration, but after the integration, the full meson-meson scattering amplitude is, first order is minus I lambda, second order is proportional to lambda squared, third order is proportional to lambda cubed. We do not use this correctly because it tells us that the scattering magnitude is infinite, because the log of an infinite number is an infinite number. Instead, measure the scattering amplitude m for given measured values of S, T and U. Feeding the result into the above equation gives minus I lambda sub p equals minus I lambda plus a term proportional to lambda squared. Here lambda p is the measured approximation to lambda and agrees with lambda to first order. In other words, lambda p equals first order lambda plus second order terms. Substitute the I lambda from this equation into this equation, and the result is the magnitude equals minus I lambda p plus a term proportional to lambda squared with an extra term proportional to lambda cubed at the end. Now, log of omega squared on S minus log of omega squared on S0. In other words, the log of infinity squared on S minus the log of infinity squared on S0 equals the log of S0 over S. And at this point, you can see why it becomes important to choose the correct infinity. If I use ordinal infinity, infinity divided by infinity equals 1, because for sufficiently large x, the value of x over x is always equal to 1. For the naive infinity that you taught in school, infinity divided by infinity is undefined. For cardinal infinity from Cantor, the best that can be said is that 0 is less than or equal to infinity over infinity is less than or equal to infinity, which is not useful. Certainly not in this case. Now, going back to this equation, because the measured value of lambda agrees with the theoretical value of lambda to first order, we can replace the lambda up here with the measured value of lambda here. And the result becomes magnitude of scattering equals minus I times measured value of lambda plus a finite term proportional to lambda squared plus order lambda cubed. In doing this, because we've been able to cancel out infinity over infinity, all the terms that include infinity have cancelled out. And this final result is the result that quantum physicists already use. So, ordinal infinity ties in with what quantum mechanics physicists are already using. It's a different way of doing it, but it's equivalent. So, take-home messages. Quantum physicists already use an ultraviolet cutoff that is equivalent to ordinal infinity. And they also use the order of magnitude calculation, big O notation, which comes from ordinal infinity. You can't get big O notation from naive infinity. You cannot get big O notation from cardinal infinity. So ordinal infinity can be used in renormalisation. Rather than seeing quantum numbers as the number of wavelengths in an interval, they can also be seen as integer factors of integer ordinal infinity. Wave-particle duality works in ordinal infinity, but not through the operation of limb star. And the Heisenberg uncertainty principle, when using ordinal infinity, has yet to be fully understood. Thank you. That's the end of this talk. The next talk will be about, well, this one is about the application of infinity in quantum mechanics. The next talk will be about the application of infinity in computer programming, and in particular in computer science. Bye for now.